Okay, so starting off, these problems, you're going to definitely want to practice these. If you're not accustomed to doing the worksheet, shame on you. But this would be one of those times where you should reestablish yourself as the worksheet working machine. A times b to the x. So we have two ordered pairs. Neither one of them is the y-intercept, so we'll just plug in. So we say at the first point, and again, it doesn't matter which one you call the first point. I'll just use the first one listed. We get 1/8 equals a times b to the negative fifth power. And you're like, that looks pretty cool. One equation, two unknowns. I'm going to need to use the other ordered pair. So at the point 4/8, that's a good looking ordered pair. Wow. Rather boring, actually. 8 equals a times b to the fourth. All right, so now we can create our system. And I'll go ahead and write system here, although we didn't do that last time. You don't need to. And I'll put the variables on the left. Again, just out of preference. So we do that. We have an 1/8. And then we do this. And we've got ourselves a positive 8. Now, you don't need to label those as 1 and 2. If you just want to do top divided by bottom, that's fine. So let's go ahead and do that. I'll just do a times b to the negative fifth divided by a b to the fourth. And that equals 1/8 all over 8. What's going to happen with our 8? Divide out. See, it wouldn't want to be you. And we get b to the negative 5 minus 4, which is negative 9. And what's 1/8 divided by 8? 64, 1/64 or 1? 1/64. Good, because that's really 8 over 1. So you don't want to mess that up. If you need to go off to the side and do stay, change, and then 8 over 1 becomes 1 over 8, it's better to do it off to the side, right? That's our bench work. And get it right than to guess and get it wrong. Okay, so now at this point, you have the negative 9th power. So we're going to raise both sides to its reciprocal, negative 1/9 power, negative 1/9 power, and we get b equals this fantastic number, 1 over 64 to the negative 1/9. Now that's one version of b, but notice that one has kind of both undesirables, right? It's got the fraction and the negative exponent, whereas in the previous problem, both versions of b had just one of those. So if you want to use that version, knock yourself out. What's another more user-friendly version? If I flip the fraction on the inside, call that 64 over 1, or just 64, what does the new exponent become? Positive 1/9. Oh, I like that a lot better. Now, before you leave it like that, just ask yourself, is 64 a perfect 9th root? No, it's not. If it were, I would just call that whatever the number would be, if it were an integer. But if it's not, we'll just leave it like that. Okay, so there's the value of b that I'm going to use. I'll put a rectangle around it, rectangle-ish, I guess. And now I'm going to plug it back into either one of these. Which one do you want to use? The second one. Yeah, look at that. I darted down at the end. It doesn't really matter, but the second one looks more user-friendly, especially for the version of b that we decided to use. So we get a times b to the fourth equals 8. And again, notice how I did that. I just left open parentheses as step 1, and then step 2, I'm going to come back and put 64 to the 1/9. Bless you all. Okay, so now I get a times 64 to the, what's a 9th times 4? Remember, that's 4 over 1, so you multiply straight across, so it's just 4/9. Yeah, 4/9 equals 8. And now you divide through by that, and you get 8 over 64 to the 4/9, which is a yucky, gross version. So as we did before, and you could actually do this in one step, you could bring the 64 to the top and call it to the negative 4/9. So in general, if you try to avoid the fractions, it might work a little bit easier for you. Just bring things to the top and change the sign of the exponent. So if you wanted, you could actually multiply both sides by 64 to the negative 4/9 up here, and you accomplish the same thing. Okay, so there's an outstanding value of a, and I'll box it too in a rectangular-ish looking thing. And then so we come down to our final statement. We plug it into the final template, and we got a, which is a times 64 to the negative 4/9. times b, which is 64, to the 1/9 raised to the x power, which remember is just times x. And lo and behold, we have the same circumstance as we did previously, meaning I can combine my bases because they're both 64s. So I'll write that as 8 times 64 to the 1/9 x minus 4/9. And of course, if you wanted to factor the 1/9 out, you could. Let's see what that would look like. Putting it into standard transformation form, you factor out the 1/9, you're left with x minus what? What's 4/9 divided by 1/9? 4. Yeah. And so here's one good-looking version, all spiffy, ready for the homecoming dance. That's in the past, I guess. And then, let's say prom. Yeah. Right? Looks all spiffy for prom. So that could be an answer. Does anyone see anything else we could do on this one before we walk away from it? We want to kind of explore it to its entirety. What's that? Make the 8 a what? It does, right? You can write 64 as a power of 8, which means you can write 8 as a power of 64. So there's two different ways to do it. I think the easier way is to replace 64 with what? What is 64 equal to in terms of 8? 8 squared. And that's to the 1/9 times x minus 4th power. And now I have a power raised to a power, which means I do what? I multiply, right? So that becomes 8 to the 2/9 times x minus 4. That would work. But wait, there's more. Now, because they're both powers of 8, what could we do? Combine them by doing what to their exponents? Adding them. Okay, so we're running out of room here. So that's going to be 8 to the, I'm going to have to redistribute the 2/9. 2/9 x minus, that's going to be 8/9, and then I have the plus 1. I'm going to call 1 9/9. So you okay with that? That's the 1. Why would I want to do that? So that I can combine like terms in the exponent. This is just getting better and better and better. What's 9/9 minus 8/9? 1/9. Good. Now I could put it back into standard transformation form, and I get 2/9 times x plus, what's 1/9 divided by 2/9? 1/9 divided by 2/9. Good, I heard it. 1/9 times 9/2. It's 1/2. And this right here is probably the prettiest looking version of that function. Would I make you do that on a multiple choice question? I don't know, but it is kind of fun. Let's talk about what the parent function is. What is it? If we got down to here, the parent function is 8 to the x, which would be growth. The 2/9 would be a horizontal what? Stretch by a factor of 9/2 or 4.5. Good. We're making it 4.5 or 9/2 times bigger. Good. And then we pick it up and move it left a half. Yeah. So this one was unique because the A value and the B value were powers of each other. The previous one we worked, they were not powers of each other. They were co-prime, actually. So, yeah. I'm satisfied with that final result there, unless someone sees something else we could do. You want to make that a power of 2? Can we make that a power of 2? You can just call it 2 cubed, right? And that would be 2 to the 2/3 power. Oh, okay. All right. A lot of fun you can have with exponential equations. All right, so where do you go to practice cool stuff like this? Corby's World worksheet, right? Corby's World worksheet. All right, any questions or comments on that? Fun, 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 or fun, 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 fun? Fun, 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 fun. We'll add one more. Fun. It is. All right, so there's one last type of function in here that we're going to look at, and it's kind of a modified exponential. If you think back to what we talked about in the beginning, of things that grow exponentially, like populations. Populations grow exponentially. Right here you have Adam and Eve, either the biblical sense or the non-biblical sense, whatever. And then you have people. So as time goes to infinity, what's happening with the number of people? The people is also approaching infinity. Now, is that a reasonable number of people for planet Earth? Infinitely many people? Can you imagine the parking nightmares you'd have with infinitely many people? Would that be even possible if we learned to inhabit other planets, infinitely many people? No. So some things that grow exponentially in the short run cannot continue to do so indefinitely. Would you agree? Yeah. Okay. So that's why we have these types of functions, which are called logistic. That's a soft G. So that's not a log function. That's a logarithmic function. This is logistic, a logistic function. So here's what the logistic function looks like from its curve. It, just like an exponential, it has a seeding value, okay, a y-intercept. That's not 0. It's going to grow at an increasing rate, just like an exponential growth function is going to do, up to a certain point. But after a certain point, it cannot continue to increase at an increasing rate. It'll still increase, but at a decreasing rate, approaching some upper horizontal asymptote that's called the carrying capacity. Okay, so like Earth might have a carrying capacity. We don't know what that number is, but it's probably there somewhere. Okay, so in this case, this is like spreading a rumor. Right? If we decided to spread the rumor that math is fun, all right, and you go spread that rumor. Maybe we start with just 2 people. If our goal was to tell everybody on campus, and just simplistically, let's just say that there's 2,000 students on our campus. All right, so that's our goal. As the rumor starts spreading, hey, math is cool, pass it on. Hey, math is cool, pass it on. This vertical distance from the x-axis measures the number of students who have heard. Would you agree? The y value measures the number of students who have heard. If you look at the difference then between the student population and the number of students who have heard, that's the number of students who have not heard. You cannot continue to increase the rumor at an increasing rate because after a while, there are fewer people that haven't heard the rumor. So they can't continue to grow at that rate. It still is going to increase approaching the student population. So we call that the carrying capacity. By the way, there's still a horizontal asymptote down here at y equals 0. Okay? It just has 2 horizontal asymptotes. One on the bottom at 0, and then one at the top at the carrying capacity. We call that y equals L for simplicity, for limit to growth, if you want to think about that. Guess where this point is right here? This is an interesting point because this is where the curve is growing the fastest. That's where it's the steepest. That's where the graph is the steepest. That's where, in this case, the rumor is growing the fastest. That's also where the curvature of the graph changes from curving upward like a cup to curving downward like a frown. Down like a frown, up like a cup. We call that point in mathematics, did you hear my voice when I said up like a cup? Yeah, it kind of inflected a little bit, right? What is inflecting? If your voice inflects, what does it mean? It cracks a little bit, right? Or changes. We call that an inflection point. It's where the curvature changes, okay? Let's write that. It's where the curvature changes. And it's always predictable, not the x value or the time value, but it's always predictable where that inflection value is going to occur for a logistic graph. Any idea? Where do you think in a population of 2,000 students that rumor can be growing at the fastest rate when how many students have heard? 1,000, which is precisely exactly half of your limit to growth. Very good. Okay? At half the limit to growth is where that is going to be growing the fastest. After that, there are more students who have heard than students who haven't heard, and so it cannot continue to grow at that rate. So these logistic curves, we sometimes call them S curves, as you can kind of see the S pattern there. So they're going to have a distinctive look graphically. They also have a very distinctive look by their equation. Here is an example of a logistic equation, okay? Is it still exponential to an extent? Kind of, right? It has an e, a base 2.718, raised to some variable power. But notice it's in the denominator now. It's added to a constant, and it has a single number in the top. Guess what that number is in the top every time? Yeah, that's your limit to growth. That's your carrying capacity. That's the upper horizontal asymptote's y value. That's y equals L. Okay? Pretty cool. So let's go ahead and work through this problem. This one's going to be entirely on the calculator, and this is also going to be resemble your free response question on your test ultimately. Okay? A horrible rumor begins to spread around the MBHS campus. Student population now of 2,000, not 200. Add another zero there. Who are the instigators of this rumor? Carlos, Petunia, and Wallace. Are those classmates of yours? Carlos, Petunia, and Wallace begin telling everybody this. Hey, titanium necklaces do not, I repeat, do not increase energy and balance. Pass it on. Do you remember the fighting phase, those titanium necklaces? You could buy the real ones at Dick's Sporting Goods for like $56. Wow, they were braided, they were blue and white, different colors. They were cool. They were marketed to increase your energy and your balance. And they worked, right. And then you could buy the knockoff brands for like $5, okay? So anyway, they're spreading the rumor that they actually work. After T days, the number of people or students who have heard this dastardly rumor is modeled by this logistic function right here. And again, notice the student population of 2,000 is in the numerator. Here are the questions we want to ask. How many people on campus originally heard the rumor? Okay, after they started it, round to the nearest whole person, blah, 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 blah. Okay, so here's what we're going to do. Our first priority, since this is a calculator question, is to, hang on. The first priority is to get this in your calculator into Y1, okay? So, go to your calculator, turn it on. It's on the bottom left. If we're out of calculators, do we have any? You might have to just look on. There you go. Hit Y equals, and let's go ahead and use the horizontal division bar. Alpha Y equals. Remember? That unlocks the horizontal division. And there it is. So you type in 2,000, double check it's 2,000 and not something else. And then down here, 1 plus 115 E. Remember, E is second ln. That's e to the power of. It automatically gives you the exponent negative 0.97. And instead of t, which is time, our independent variable is x. Click to the right a couple of times, and then double check, triple check, make sure that it's exactly as it's supposed to be, because you're going to rely on that to answer the rest of the questions. How does it look? It looks good. Now, if you hit zoom 6, you're going to be like, I don't see an S-curve. And I'm like, very good. You shouldn't really. Okay? So you're going to have to establish your own reasonable window. So let's think about that. What are we measuring on the x-axis? We're measuring time, right? What is a good lower bound for time? 0, right? Now we're measuring time in days. How many days do you want to expire or go by before we analyze it? You want to go like 10 years, or you want to go a day or 2 weeks? That's T epsilon. Let's do it like this. 0 less than or equal to T is another way to do it. 2,000 days? Oh. Let's try, you want to give it 2 weeks? Let's try 2 weeks, okay? Let's try 14 days. So I'm going to set my T min or X min to 0, my X max to 14. What are we measuring on the Y-axis? People who have heard the rumor. What is a good lower bound for people? Lower bound. How about 0? Yeah. And what would be a good upper bound? Yeah, 2,000. Now, I would recommend something above 2,000 slightly, because your calculator uses the very top portion of your calculator to write letters, to write numbers. So if you go to 2,500 or 3,000, you should be good. All right, so that's going to be our Y min, Y max. So let's go to the calculator. Under the window, let's go from 0 to 14. Now, we're just guessing on the 14. We're doing trial and error on the X max. X scale, 1 is fine. Y min is 0. Y max is, I'm going to go to 2,500 instead of 3,000. But we know it should at least include 2,000. So the only thing we're really kind of guessing on is the 2 weeks, the 14 days. Now, if you hit graph, look to see if you see an S-curve. Do you see one? Oh, it looks beautiful. Right. So at this point, look what would happen if you went out to, let's say, 350 days. You're like, okay, that's a little long, right? The S-curve is going to manifest a lot, so you can shave some off. You can shave some off. If you didn't give it enough time, if you just called it like 1 day, now you're like, I need to look a little more to the right. So you can kind of adjust it until you find a reasonable upper bound for X where you see the S-curve. But here's the golden rule. Do not start answering questions until you see the S-curve. Because if you don't see the S-curve, either you're in the wrong window or you have it typed into your calculator incorrectly and your answers are all going to be wrong. Yeah, R-O-N-G, wrong. So for calculator questions, you're going to get to use your calculator on this next test. Yay! There's a certain etiquette that you have to have on your paper. So here's what I expect to see. How many people originally heard the rumor? Originally corresponds with what time value? 0. So here's what you need to show on your paper. R of 0. That's it. Or whatever the function's name of 0. That's all you have to show. And now on your calculator, you could do it either from the graphing screen. You could hit trace, type in a 0 and hit enter, and it has it right there. It said to round to the nearest whole person. So here's the 3 decimal exception. It said to the nearest whole person, so that would be how many? 17, okay? So we can go and write that down. 17. You could put students, people, or rumor mongers, whatever you want to write. Now, the other way to do it is from the home screen, remember. If you are in your home screen mode, you can hit alpha trace and then recall what's in Y1. If you open parentheses, type in a 0 and close parentheses, you get the same thing without the visual. Okay? Remember, if you're going to use the trace command, your X value has to be in that window. And 0 was. It was our lower bound. All right, so this would get you full credit on a test. If you're missing any of that, you're not going to get full credit. Got it? So the 3 started the rumor, but at time 0, when the rumor really got going, there were actually more people involved, 14 others, co-conspirators. Part B, to the nearest whole person again, find the number of people who have heard the rumor after 1 day, 2 days, and 5 days. After 1 day, after 2 days, and after 5 days. Are we going to do this any differently than what we just did? No, okay? So I'm just going to keep doing it from the home screen. Second enter. I'm going to scroll back here and change this 0 to a 1. What should I write down, 44 or 45? Either one. Remember, you can round or truncate to the nearest whole person. So 44 people, but stick with 1, okay? Don't put 44 or 45. Just pick 1 and go with it. I guess if I'm using students, I should keep using students. Rumor mongers is kind of a long unit to use. On day 2, actually, let's go back to the graph. If you want to hit trace to enter, you can do it that way if you want. That's 114 students. This one you get the nice visual. And then on 5, you're in still trace mode. Just hit 5, enter. It's a little faster. 1,052 students. Cool. So you write all those down with units. You think you could do that on a test, get full credit? If you're missing any part of that, you're losing points. So far, so good. Pretty easy, right? But notice how the rumor's spreading. We spend money. Okay. So these are easy. These are the types of questions where you are given the input. Real easy. It's plug and chug. Just type it into the calculator for X. But look at part C. How many people have heard the rumor when the rumor is growing the fastest. How many people have heard the rumor when the rumor is growing the fastest? Do you need to show any work for that? Not really, because what did we already say? The rumor is always going to be growing the fastest at the halfway point, people-wise, which is what? 1,000. So all you have to do is answer it like that, 1,000 students. Or you could say the rumor is growing the fastest when 1,000 students have heard. But you could just answer it as 1,000 students because it was a direct question. But there's a follow-up to that. On which day did that occur? Oh, well, from our data on Part B, we knew it happened somewhere between day 2 and day 5, correct? But that's not good enough. So now 1,000 students is not an input. This is an output. Essentially, we're given an output. You had to tell me what that was based on your knowledge of the function. So that's a y value. So instead of setting it equal to 1,000 and algebraically solving it, here's all you have to do. You show me that you're taking the function r of t and you're setting it equal to 1,000. Now you can either write r of t equals 1,000 or you can write this whole mess equals 1,000. Which one would be easier? R of t, that's its name. Okay? Now the way that you're going to solve this is graphically. You're going to go back to your calculator and into y2, you're going to graph, guess what? R of t. And the solution should be where the two graphs do what? Intersect. Boom, right there. I can see that that's the what point? What do we call that, where it changes from increasing at an increasing rate to increase at a decreasing rate, where the curvature changes? The inflection point. Good. And so all we have to do to find it is go to our calculate menu. If you hit second trace is your calculate menu. And look at those delicious choices on the menu. Right? It's better than the Wendy's dollar value meal. Which one do we want, do you reckon? Intersect. So number 5. It's going to ask you, is this the first curve? And it's blinking on one of them. All you have to do is hit enter and say, yeah. Okay? You say yeah in your head. Don't say it out loud. You'll disrupt people. It'll automatically put you on the second curve and says, is this the second curve? And you're like, yeah. And now for the guess, all you have to do is say 7 and hit enter. You actually don't even have to guess. If you just hit enter, because there's only one point of intersection, it's going to find it. If there was more than one point of intersection, second trace number 5, enter, enter, then you would want to make sure on the guess that you're scrolling closer to the one that you want if it intersected more than once. But if it only intersects once, when it asks for your guess, you can just hit enter. You're not going to really speed up the calculator by moving closer to it. Just hit enter. And there it is. Now, did it say to round to the nearest day? Let's read. Did it say to round to the nearest day? It just said on which day did it occur. So we could say t equals, and then let's go ahead on which day did it occur. What day would that be? On the 4th day? Here we have to be careful. We don't truncate here because this is 4.89 days. That means 4 full days have already taken place, and we are 89 hundredths already into day 5. Does that make sense? So this occurred on day 5. Yeah, on day 5. T equals 5 days. So make sure you put units. All right. Now the other type of thing is if I did not ask to round to the nearest day, you would just put t equals 4.891 days. All right, but you don't want to say both of these, okay, unless you want to say 4.891 days, which is approximately 5 days. You're just reading my mind, yeah. What if that were just 4.091? Would that still be on day 5? Yes, that would be like early morning day 5, like at midnight 02, right? So you have to read the question kind of carefully. All right, but it's not that bad. You see how we're doing it? We're setting this up. This is going to get a check, and then you're going to get a check for your answer, and then with the units, possibly. Pretty easy. All right, so now there's one last one to go. Describe, and this, by the way, works for any time. If I say, on what day did 1,500 people find out, right? You just say R of t equals 1,500, graph it, see where it intersects. So when you're given an output, you're going to graph the output in Y2 and then find the intersection. Second trace number what? 5. Yeah. Okay, now the last question here. Describe the end behavior of the graph. What does it mean in terms of the rumor? So here's how we're going to describe the end behavior. It's the limit as time goes to what? If we let this rumor go on and on and on towards infinity of R of t, what is R of t approaching? It's approaching 2,000. Yeah. That's the upper horizontal asymptote. And we'll put students there. Now, here's where models can kind of be practical, but not perfectly for theoretical purposes. Because in theory, will that final student, the 2,000 students, ever hear the rumor? Will that graph ever hit 2,000? No. So you could go like 80 years later, and that guy's like he's like a 100-year-old man, and he's like, I remember something my senior year, they were saying something about fighting, but I'm still in the process of learning, right? That rumor. It's still coming to me slowly, right? He'll never fully get the rumor. But in practicality, will the entire student body find out? Yes, okay? So there are limitations to mathematical models. We use them to predict, we use them to interpolate and extrapolate, but we always have limitations, okay? So that's it. That's how you do a problem like that. You're either given an input or you're given an output and you graph it, find a point of intersection. Do you think you can handle that? Don't answer any questions until you graph it and see a what? An S-curve. All right. We're done. We are done. Tomorrow, Mr. Falcone is going to come observe. We're going to start the next section. I don't know if he'll be in this class, second period or third period, but we are going to start the next section tomorrow. So no quiz tomorrow. All right. We'll probably quiz on Thursday. Make sure you do the worksheet. Tomorrow is Halloween dress-up day. No masks, right?